so I'm seeing we should probably get started on this panel. We have a lucky 42 people in the room. That's the perfect signal. So thanks everyone who's joining us via various media. I'm Adam Chapala from MIT, one of the organizers of our virtual workshop, and I'm glad to be able to moderate this panel, which is on the subject of proof assistance for both math and programming languages. And I'm going to briefly introduce our panelists and then give each of them, let's say, 3 minutes for opening statements, and then we'll go into the mode of having them answer questions, both some that I've prepared and some that you can ask us live with the Q&A feature in AirMeet. So I'll just try to multiplex between those in some sort of appropriate way. So without further ado, I'm just going to go in alphabetical order here. I'll start by introducing Kevin Buzzard, who's a professor of pure mathematics at Imperial College London. He specializes in algebraic number theory. He's won the Whitehead Prize and the Senior Berwick Prize from the London Mathematical Society. And just long enough ago, like the perfect length ago, he got into proof assistance. Recently enough that he still sees some of the biggest challenges and is coming from a perspective of his native field of math, but long enough ago, 2017, that I think he's had a decent amount of time to put different tools through their paces for applications in pure math. So we'll come back to him saying more about his perspective in a moment. We also have Favonia, who's an assistant professor in computer science at the University of Minnesota. He works in proof mechanization, type theory, and programming language theory. Probably one of his topics most relevant to this panel is cubical type theory, but he also has broad interests, like he has a paper on testing at the POPL'22 physical conference, the counterpart to this virtual workshop. Then we have Zhong Shao, who's a professor of computer science and chair of the computer science department at Yale. I think of him as one of the first users of proof assistance in the POPL community who wasn't also an author of a proof assistant. Starting from work in functional programming, he transitioned into verification of computer systems. Probably best known result there is on the Certicos operating system that has spawned a bunch of related work in topics like compiler verification. He had some related papers at the main POPL conference and previous editions of it. He's also co-founder of a startup called Certicay, which looks at smart contracts. And finally, in alphabetical order at least, Nicolas Tabareau is a senior researcher at Inria and is the head of the Galinet team, which is focused on enabling next generation proof assistance. He's involved in the homotopy type theory effort. He had a distinguished paper at this POPL about subtleties of a kind of equality in type theory, and at the previous one about integrating computational rewrite rules inside a type theory. And I was surprised to see on his webpage, he may be one of the few people in the world who can say he's interested in cognitive science and aspect-oriented programming. So maybe I'll go through this list again in alphabetical order and give each of the panelists a chance to spend about 3 minutes introducing their perspectives and what they see as some of the maybe most interesting topics for us to drill down on later. So let's start with Kevin.
So hi, I'm Kevin. I'm a professor of pure mathematics at Imperial College London and algebraic number theorist. So in algebraic number theory, nobody uses theorem provers. We do all our work with pen and paper. We don't really use computers to do much on the theoretical side, although people sometimes use them to grind out computations. And a few years ago, I decided to experiment with proof assistants because I was interested in using them for teaching. But then I saw a talk by 2 weeks into my experiment. I saw a talk by Tom Howells at the Newton Institute, where he suggested we should be using them to do serious research in number theory and other areas of pure mathematics. So that got me very inspired and fired up, and I started thinking about these things from a research point of view. And at the time in 2017, I was absolutely shocked and horrified by the state of the system and the kind of mathematics that people were doing. It felt like a million miles from the kind of mathematics that was being done in math departments. And I said a number of things quite loudly and upset several people. And I've spent some of the remaining part. Since then, I've spent a lot of time apologizing for these things. So I'll apologize again for some dumb things I might have said in 2018 and 2019. But now I'm a firm part of the community. I'm using Lean to do research level algebraic number theory. I mean, I'm not using it to do new mathematics, but I'm using it to I'm translating other people's mathematics into Lean. But it's the kind of mathematics that the math community is very sort of receptive toward. And I'm very interested in seeing how we can get theorem provers engaging more with research level material in areas like number theory and algebraic geometry, and the kind of areas that haven't been traditionally somehow used, somehow formalized in these systems.
Okay, great. Favonia, why don't you go next?
Hi, so I'm Favonia. I'm a assistant professor in the University of Minnesota. And I actually have been thinking about what kind of message I should put into my 3 minutes talk. And then I think my message is actually more like a meta one. So we have been building different kinds of proof assistant and trying out different ideas. I'm also myself also a active user of the EGDA. So what I learned from building those proof assistants, so far I have been involved in building at least 3 of them. What I learned is that it's very important to contradict yourself, at least your past self. And so I feel it's crucial to just be very open-minded, to admit that maybe some of the ideas you hold dear in maybe just last year was actually not so great. And it's kind of, well, my point is that you have some theory and something that you want to try out, and those things, those ideas, and can be then verified and evaluated with practice and experience that you gathered. And it's really crucial to understand that maybe some of them actually are not as good as you thought they would be, and just admit that, okay, they are bad and move on. So I feel that any pride that is attached to a particular idea or theory could be a hindrance to progress. Maybe that's the message I want to convey.
Was that about proof assistance in particular, or just advice for doing science?
Maybe I see the science from doing proof assistance.
Yeah. Okay. Yeah, fair enough. Let's all keep our open minds and write lots of code. I like that message. Okay, over to you, Zhong.
All right. So my research team at Yale has been working on developing certified OS and a compiler, mostly using Coq. So I mean, overall, we are just trying to develop compositional techniques for specifying, implementing, verifying all these kinds of software or hardware systems. So if you look at the current mainstream OS compiler platform, we rely on something called ABI, or Application Binary Interface, to compose the components from different vendors. So these, you could have something for x86, something for ARM, or something even for a Java virtual machine or some other virtual machines. So ABI is kind of like a common format. And then naturally, for the ambition for those who work on certified OS and the compiler is whether we can have something for, ABI for certified applications, right? And then we can, so the question that I want to raise is, how do we define such certified ABI? And because we need that in order to facilitate this community of, composing and building large-scale certified softwares. So there's a lot of questions surrounding what this ABI should be like. But the one most related to this panel, of course, is what should be the proof certificate look like? What should the proof object be like? Is there some kind of a shared core logic or shared common logic or core logic which we can use? And how do we reduce the size of a proof objects if we plan to include the proof objects in this kind of a ABI files, right? So this is not necessarily very deep theoretical question. It's kind of like to some degree, it's a engineering question. It's not necessarily that hard. In fact, we are not trying to find the world's most general logic or anything. For many of our software verification, we only need a pretty simple logic, something non-controversial. And we all know right now our community is kind of divided based on which proof assistant you use, right? Which theorem prover or SMT solver you use. And even within each proof assistant, we often use different semantic model with different program logics. So we're kind of divided. So what I think is, what would be incredibly valuable for our community is to have such a shared core logic, which can be something non-controversial, something like lambda HOL, or in Coq, it could be just prop plus type 0, type 1, and plus inductive definitions. And then you try to have a common format for this and try to map different proof assistants related concepts into this same format. And then, you can have different proof assistant offer the possibility of generating such a proof object. And the proof checker can be made extensible. Basically means you can have, the very naive foundational proof checker check these proof objects, but you can also have a certified tactics or extensible tactics that can be checked on its own. So you can basically build up your tower of proof checkers. Kindergarten math proof checker, the high primary school math proof checker as we build up. There's some work we did along this line a while back in our project called VeryML. But overall, it would be great if we have such a thing. So that's like one of the I would say not too high hanging. It's pretty low hanging things that if we have such a thing, then it will greatly help the community, basically. That's it.
Thanks. I can definitely agree with that call to action. And let's go to Nicolas finally.
Hi, so I'm Nicolas Tabareau, a researcher at Inria in France. So as Adam said, I'm mainly working on the extension of Proof Assistant and in particular Cork. And more recently, we've been working on the MetaCoq initiative, which is a particular approach in which we formalize in Coq the type checker that we define for Coq, and also in the future for extension of Coq. And so today I would like to talk about the future of Proof Assistant in the prism of so now we are quite, I think we all agree that they are quite mature, and we already believe that we can formalize a huge part of mathematics and use them in both mathematics and computer science. But I think we have to be careful to make this huge human effort really useful, and not to waste our time in stuff that will be not available or destroyed or deprecated later, and not usable anymore. So for instance, we have several issues to attack on these lines. So first is scalability. So we need to make sure that will not be blocked at some point by making things bigger and really reaching barrier that we cannot go through. Another issue is the structuration of, for instance, algebraic hierarchies. We also need to make sure that by building bigger stuff, we'll not get lost and not get lost in the system, not being able to know which structure we are using and what is the definition of this multiplication symbol and so on. So we need to make sure that we can keep our feet on the ground on this. And more stuff. So we have the issue of maintainability. So for example, there is the recent story of Lean 3 and Lean 4, and we also how to port stuff that have been done in one version of the proof assistant to another one. There is another vision of this with Coq's policy of making things more backward compatible, but it has also other drawbacks. We have also the issue of interoperability. So maybe that's what's connected to what Zhong was saying, that maybe it would be also great if you don't have to marry to one particular proof assistant, and you can reuse libraries developed in other proof assistant by being able to reuse at least the proof of the theorem in your favorite proof assistant, because it has been tailored for your need. But maybe you need, as you do in mathematics, you can open another book and you can reuse the theorem of this book, even if it has not really been written in the same way or organized exactly in the same theoretical setting. And maybe so it's a bit less connected, but also we have the issue of making all of this quite green with respect to environment. So if we make things very big, and if we make sure that each time we modify the system, we have this continuous integration system that's checked that all the big libraries that we have been developing on mathematics and computer science still works. So for now in Coq, it's usually it's already quite huge. I don't know what's the situation, for example, of the math library in Lean, but if we recompile everything all over again and again, maybe it's not really good with respect to environment, and we should find some other ways to make sure that we are building stuff, and we can add another rock on the pyramid without recompiling everything all over again. So maybe a green consideration would be good to have for this meeting.
I was not expecting to hear that phrase in this panel, so thanks for confounding expectations. Yeah, maybe we could come back to that one too. Okay, great. So I'm going to start by asking one of the questions that I prepared, and then that'll give folks a chance to post their questions in the Q&A section of AirMeet. And we also had at least one question on Twitter already that I'll come back to. But let me kick things off with the following question. What are the most important differences between how proof assistants should be used in programming languages versus math? Can we learn anything about new features in proof assistants that would be helpful for one of those two application categories, but aren't present because maybe the people building that proof assistant have been thinking of it mostly from the other perspective? We don't have a great bus control mechanism here, so I would just suggest people unmute and speak up, and if necessary, we can back off.
So it would be, one thing I'd like to talk about would be quotient, because this is something that mathematicians use everywhere. But my understanding, I'm not a computer scientist, but my understanding is that there are people, especially in the COP community, who are quite unhappy with Lean's approach to quotients. And this is something I don't really understand, but the developers of Lean have built quotients into Lean in a certain way, which makes mathematicians extremely happy to use them. But as I say, seems to have some kind of type theoretic issues which don't bother mathematicians but bother computer scientists a lot. So that might be one. I mean, I suspect that Nicolas might be able to say something about the problems with Lean's quotients.
Yeah, so as you say, it's really meta-theoretical consideration. So actually, Adam has cited our distinguished paper this year at POPL', and it's providing an extension of CIC with a setoidal equality in which we can have quotient. So we hope that we'll be able to have them in Coq in the way we want to integrate them. But from the outside point of view, they will be very similar to the one that are developed in Lean for the moment. So it's just that Lean is ready to Lean developer and are ready to quit some good properties we really believe in strongly in the Coq developer among Coq developers, but maybe they're not that. I mean, that's important from a mathematical point of view.
You're thinking about different kinds of questions to the kind of questions that I think about as a number theorist. I suspect it is. Because I must be absolutely honest, I don't really understand the objections. I just want some quotients.
Like, Nicolas, could you imagine some kind of proof someone might want to do in number theory that would go worse because of the way that quotients are implemented in Lean versus with alternative proposals that you favor?
No, it's a more general concern that if you don't have a strong canonicity result, you're not guaranteed that if you have proven. So it's somehow the same. I don't know if you know the issue with cubical type theory, and so there is a number we call it the Brunry number because it has been defined by Guillaume Brunry, and it's supposed to be 2, but when you evaluate it, for some reason we don't really know if at some point we'll get a result, but if you wait long enough you don't get any result. And Guillaume has been able to prove that this number was equal to 2, but you cannot evaluate it and get 2. And if you have this kind of canonicity issue with quotient, it could be the same, that you define using quotient and stuff like that an integer, and when you want to evaluate it, you don't get the value because it's blocked by some issue in the way quotient or the elimination rule is defined and so on. And this we really want to avoid it, but maybe there are workaround and you can still prove that it is equal to the number that you want, and then you can rewrite. And
exactly. So, this is something that when we were preparing, this is something that Adam, a question that Adam emailed earlier. He says, why do these theorem provers sometimes take so long to evaluate a term? And I think that one of the ways we use this number, this pi4 of S3, this has been known by the math community to be 2 for many, many decades, because we have a proof that it's 2, and our proof does not involve constructing an incredibly large term and then attempting to evaluate it. Our proof just involves lots and lots of rewrites. And because we do not think of mathematics, because we're not constructivists on the whole in the mathematics community, our instinct is not to attempt to prove that this number is 2 by computing it. Our instinct is to prove that this number is 2 by reasoning about it. And so the fact that it's difficult to compute for whatever reason, a lot of Lean's maths library is completely non-computable. We don't even have computable polynomials. You can't evaluate the product of 2 polynomials. You have to use your tactic, which uses rewriting to compute these things for us. So this quotient issue might be a special case of a more general issue of, how does one prove that A equals B? Does one attempt to prove A equals B by REFL, or does one attempt to prove it by SIMP, by a series of rewrites? And my impression of the computer science community is they want to prove a lot of things by REFL because REFL is computation, and they're interested in computing. But with coming from the mathematics side of things, that's not necessarily my first instinct about how to prove A equals B. I want to apply theorem after theorem after theorem and get there. And in some sense, that's why mathematicians can prove that the Brunry number is 2, but the computer scientists can't.
So I agree with you. The only issue is where is the frontier. So at some point you may want to reuse some mathematical theory and some theorem to produce a number that you really want to use in a program, let's say on an airplane or whatever. And if you don't have the guarantee that the mathematical theories that you have been using will already produce a number in a finite and reasonable amount of time, then it makes your algorithm useless. So it's not only about proving equality, it's also about getting a result when you want to evaluate your program. Yes, and the frontier between programs and mathematics is really weak now. So if you're ready to say, okay, it doesn't matter if my proof of my theorem doesn't compute, then you're also close to say maybe if my program doesn't give me a value, it's okay, and this is more problematic. So
yeah, but I think that this is where mathematics is now. Coming as someone who did 30 years of research in number theory, I mean, ironically, in number theory, we don't really use numbers too much at all nowadays. We just tend to be proving abstract theorems, the form this vector space is isomorphic to this vector space, and we don't care if we can't write down the isomorphism. So some number theorists use computers, and for those ones they will need to compute. Some number theorists do consider questions about numbers, but there are other people that call themselves number theorists but never look at a number at all. They consider abstract infinite objects, and for those objects, we don't. It's meaningless. They're non. They're uncountable. One can't compute them at all. And I do think that this is. I think this is part of a general issue. There's people that want to compute, and in the math community, there's a whole bunch of people that really don't need to compute. And these are the mathematicians who are doing hard research, but are not using computers at all in their work. They do everything on pencil and paper because they're doing everything using reasoning. I've said quite enough, I think.
Yes, maybe we can move on to another question. I think actually the most upvoted question in AirMeet at the moment feels to me like it was just answered, but people can use the text chat if they disagree. But there was a request to explain what's wrong with quotients in lean. I think we've kind of been there. And therefore, I'll take the...
Just summarize it in two. There's something about subject reduction or canonicity or something.
I like that summary. So then let's take the second most upvoted question, which is now appearing on the stage. It's about promising directions for encoding algebraic hierarchies in, let's just generalize this to any proof assistance of your choice. Anyone have strong opinions here?
We're just building one with type classes, and it's just beginning to creak at the seams. It's interesting. We're running into type class diamonds where things are provably equal but not definitionally equal, and our algebraic hierarchy in Lean is gigantic. In Lean's maths library, it's absolutely gigantic now, and I do wonder whether we are going to begin to run into scaling issues. So that's not the promising direction. We're just sort of forging ahead, putting more things in it every day. And I do wonder whether we're going to start running into problems sooner rather than later.
I've certainly had issues with related points in programming languages settings, like thinking about different kinds of configurations for a compiler. So I think there's definitely some research left to do here. Anyone else have a favorite solution or a problem to mention at this point?
Yeah, that's also an issue with there is a scalability issue, but also a backward compatibility issue. So I don't know what's the situation between, for example, Lean 3 and Lean 4, but if you rely too much on proof search and this kind of stuff to make your hierarchy usable in practice, then you're not really robust, and minor changes can break everything in your, at least in Coq. I don't really know how it is implemented in Lean. So we need something that is efficient, but also that is robust and that scales. So I'm not sure that we have a good proposal for the moment. That's really a research direction for me, but an important one, because it's pretty useless to make things bigger and bigger if we can't find our way out of it afterwards. So
I should say that the type class system, the Lean developers looked at what we mathematicians had done with Lean's maths library, MathLib, in Lean 3. And one of their reactions was to completely rewrite the type class system in Lean 4. It's an internal change. And I'm not really an expert in these things at all, but when Lean 3's maths library is ported to Lean 4, it will be very interesting to see if problems have been solved or if more problems have been created. I think experiments have been done to indicate that the Lean 4 system is supposedly better, but is this afraid the proof of the pudding will be in the eating? That sounds like a very British phrase. We shall see.
Okay, going once, going twice for any other answers to this question. All right, marking as answered. We solved type classes. So let me try one of my prepared questions next, which is, which kinds of people or user personas do you think should be using proof assistance once we've worked out all the kinks and figured out the the best way to put them to work. Will proof assistants ever be part of the standard tools of a software engineer? Or will we ever assume that any PhD thesis in pure math should include mechanized proofs?
So I can say a little bit. So, more on the standard software engineering toolbox. So I hope we will see more specification languages. It's it's an old topic. Specification language have been developed, in the past, but now we can do more. I think there's a great need for our regular software engineer try to write some type of specifications for some subset of their software components. And you hope there will be some kind of a smart type checker that can check these specifications. And, hopefully they will generate some obligations that can be either discharged by automated theorem prover or some manual proofing proof assistant. And there will be compilers that can compile these specifications directly into some certified code or the certified ABI format, like I mentioned before. So I see that's one path towards the kind of a usage scenario for proof assistant. That is, you don't the regular engineer does not have to directly use proof assistant, but only use proof assistant to discharge some hard theorem, and even they could make it something that the community can help if they really cannot prove something. So that's at least the more practical side of the usage for proof assistant.
Got it. So you're saying specifications are the important starting point, and
Yes.
it might lead into doing some proofs. Yeah.
And maybe the situation is pretty similar in mathematics. So I know the Perfectoid initiative in Lean, which was just to provide an understandable and clear definition of Perfectoid, if I'm right. And I think that's really something. So it's really connected to what Zhong is saying, but on the mathematical side, that maybe the PhD thesis, it will not be formalized in for every PhD student in mathematics. A formalization of the material is too much, but at least to have all the main statement and definition expressed in some kind of proof assistant as a formal language, to make sure that other people can get access to all the definition and everything is precise. This is kind of a reachable goal, which is already quite nice. And then if you want to fill the hole, then it's another subject, but it's maybe less important because they already have the proof, and in mathematics the proof is already enough, as Kevin is saying. But maybe make sure that people understand exactly the definition and the many implicit that you can have in sometimes the definition would be interesting.
So the reason that the Lean community formalized perfectoid spaces was in some sense a response to this. Was an idea of Hale's. Nicolas is really reminding us that in 2017 Hale said, why don't we formalize all math definitions and then we can start writing down the statements of what we believe, something which would be much, 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 much easier than writing down the proofs of what we believe, like stating Fermat's last theorem and proving it. Are two very different things, and I think that this would be a very useful goal to move towards. But on the other hand, I think it's a hard sell to the math community. I think the answer to Adam's original question, are we going to see PhD theses in 20 years' time all having a formalization aspect in? I think that's absolutely not going to happen. I think there's a large resistance to. Some people get into math because they don't like computers, right? But they don't like computing. I've found it's a really hard sell getting mathematicians to use these systems. This is why I do a lot of work with young people, because I think young people are a lot more receptive to the idea of using computers. And so I'm sort of playing the long game. Eventually the old people will die out and the young people will come along, and if the young people know that it's there, I think what Nicolas suggests is a great happy is a midpoint where theorem provers can meet real research mathematics. At the minute, it's just too difficult to formalize it. But if we could persuade mathematicians to start stating their theorems in lean, or any, I mean, I say lean because I'm so used to saying the word lean. In every proof assistant, if every proof assistant had such a library, or every proof assistant interested in mathematics, then I think this would be an interesting step forward. But to ask that PhD students start formalizing proofs, we're still a very long way off.
Kevin, I cannot just add that in my experience, I have seen computer programmer hackers who don't want to do math, but they can only do math in proof assistant because they thought they are still writing code. So it's kind of funny.
It is. We are two very different communities, and it's been very interesting meeting people from your community.
And to me, the proof assistant to help people doing proof. So theoretically, all kinds of people who are doing proof potentially using proof assistants. Right now, I understand that due to maybe the funding structure and how the discipline are set up, its main application is in the computer science, in mathematics. But I can also imagine that, for example, people are doing analytic philosophy or whatever, anything that rely on kind of rigorous reasoning or whatever, they could be potential users of a proof assistant, and we could potentially develop tools for them. But it's still important to take care of the application we have now. So anyway, I basically agree with all the concerns. I just want to point out there could be maybe people outside of the computer science and the traditional community for mathematicians that could also be the users of proof assistants.
The problem with selling them to mathematicians is that a very natural response is, we did mathematics for 2,500 years without proof assistants, and it's not entirely clear what they're adding, especially when the situation right now, of course, is that they're impeding our proofs. They're not assisting them at all right now. It's up to you guys to solve this. But right now, it's harder to prove something in a proof assistant than it is to prove it on paper. I mean, not least because you can you can get things wrong on paper and nobody notices.
So maybe that's less proof assistants and more proof guardians. That's what you're saying we have today. Okay, some great answers there. Let me take the next most upvoted question. Here it comes. This is about the common characterization I hear about mathematicians, that there's a lot of abstract thinking and intuition building independently of coming up with the completely rigorous proofs. And to the extent this is true, as a description of what mathematicians do, how do we characterize the value they get out of using a proof assistant?
So Peter Scholzer is a Fields medalist, and he wrote a blog post a few months ago, now published actually, in XMath, where he flags two specific things. So he challenged the proof assistant community to formalize a proof of one of his theorems, and the lean community responded and did it. And he flagged two things that he personally got. Firstly, I mean, he got the assurance that his proof was correct, and this was an issue. I mean, well-established theorems, if the community is happy with them, then this is fine. But this was a brand new theorem that hadn't even been through the refereeing process yet. So he somehow quickly got some evidence that he'd not made any errors. But also he made the claim that the process of formalizing it and talking to the formalizers as they did it gave him a deeper understanding of the proof. I think his words were that the formalization process made him understand what made the proof work, which I thought was a very interesting thing to come from, essentially, a genius. and also as a side issue, the proof was simplified. There was a part of the proof that looked very complicated, so there was a definition that was going to be hard, and so we had to start writing down. We solved the definition, and every time we needed a property of the definition, we just formalized the statement of the property and used that. And at the end of it, we could see exactly which properties we needed from this definition. And then Johan Kommerland, leading the project, he then wrote down a definition of something. He wrote down a different definition that had all the properties that were required by the proof, and the different definition was much simpler, and we could use that instead. So there's some very concrete answers to that question, I think.
Anyone else want to say anything in response to this question?
So I think I can add something, like continuing Kevin's comment. So the four-color theorem that has been fully mechanized in Coq. In fact, if you look at the paper, they actually come up with a very nice combinatorial description of the graph. So it's not just doing the old proof. No, it's, in my opinion, it's actually a very nice new proof. And also in my own paper, there was once a case that I think Mike Shulman showed me a very good, interesting proof in a homotype type theory about the Van Kempen theorem. And I mechanized it. And I told Mike that, by the way, I never used this assumption. And I just delete that. And then because the proof assistant, I just rerun everything and it's still type checked. And we realized that we actually don't need that assumption at all. So yes, I think that already in my case, I learned a lot from just by using proof assistant.
All right, great. So since we opened the things up to Twitter to send us questions that were good to ask here, I should ask one of those that came in. So let me relay a question from, not sure how to pronounce the name, Brandon, something like that. Who wants to know, what role, if any, do you think automation should play in the design of proof assistants? And how does proof complexity influence your design? Can you provide some examples of design choices you have made that explore the trade-off between automatability and usability expressivity? So for instance, there are some decidable logics that can bring a lot of mileage for audiences who haven't been trained in mechanized proof, but there's a ceiling on what interesting things they can prove. And then you have ZF set theory, higher order logic, whatever, where obviously we're not going to get very far with universal automation, but we can say a lot more. Any thoughts about that question?
Okay, if no one starts, I will start. The experience I've learned from building a 3 type theoretic based proof system is that beta and eta rules are a must. Those two, the beta and eta rules must be automatic, period.
That's probably not a very controversial statement
But
for this
beta,
crowd.
eta,
Okay.
iota too, right? If you have an inductive definition.
So, there are also other rules and yes, so I'm talking about more like a slightly beta is of course yes, but the eta sometimes there could be some controversy. I don't think there's any technical difficulty at all to implement eta rules, and I think they should be just included.
So
Sorry.
okay, so I will just add that I think the automation is extremely important, and it's a pity that we don't have a nice integration between popular SMT solver and our proof assistant. I'm aware of all those work like Coq SMT and so on, but we should be able to do more. And I hope the proof checker that we normally use can be made smarter. I mean, we know how to build a stack of system software, right? Build OS from lowest level and get all the way to the system core. We know how to build compilers from, that contains many stages of compilation from the lowest level language all the way to very, very high level language. Even after we build a C compiler, we can build a front end compiling a particular programming language to C and then you get a more sophisticated compiler. So I think we should have a more sophisticated proof checker that involve all kinds of other tactics and decided SMT solvers and on top. Why? So that you have a smarter checker, and the checker can be getting smarter, but without increasing the TCB. That is the extension you build on top of the base checker. You have a dumb checker down below for your core logic, but you can add these extensions rules, which what Favonia mentioned that beta iota or beta eta is clearly something that's automated in the cock proof checker, but you could make them explicit, but the proof objects will be huge. So likewise, you can add many reduction rules on top without increasing TCB or violating the consistency of the underlying logic. And this kind of work has been done in the community. We just haven't exploited it as much as we should. And I think we should.
So you want to make it possible to add a call SMT solver reduction or term somehow and have it be justified.
SMT solver is too ambitious, but just as small decision procedure, type checked, type safe decision procedures on top of the checker, so that if the checker terminates, then you are sure that you will get a proof object, because the tactical decision procedure you wrote is formally verified or type checked, that if it terminates, it will generate a proof object. But you don't actually generate the proof object because the meta theory will tell you when it exists.
That sounds like proof by reflection so far.
Sure, yeah, there are flavor of that, but it's along the line of what we did in the VariML project, basically.
Got it.
Lean 3 has a very primitive SMT solver, which nobody in the math community ever really used. I think Leo Demara, who wrote Z3 and Lean, I think he was quite surprised. We tend to use the simplifier a lot. We tend to do lots of rewriting, but it's a rather neglected thing. I do wonder whether, given that Demara wrote Lean and also Z3, I wonder whether he'll consider in the future integrating them more closely.
Just to complement a bit, there is this Coq platform now that I just noticed that now there is a Z3 integration of this. So there is a plugin to make use of it. So it's work in progress, and with the Coq platform, it's easier to get everything integrated and without crazy dependencies and so on. So it's going toward this direction. And also with the MetaCoq initiative that I was mentioning, the idea is also to be able to define tactics that can be proven correct, and then when you run it, you don't have to generate the proof term, as you said, because you know that it exists, and you just need the result of the tactic. Like, just if he says okay, then you find you don't have to store anything and to retype check anything. So that's really a direction that we want to follow, but it needs a bit more time.
All right, let me take the next most upvoted question in AirMeet, which is about the biggest gotchas for mathematicians getting started with proof assistance.
At the very beginning, this is a very easy question to answer in some sense, that a beginner mathematician gets frustrated because it turns out that mathematicians do not think at all clearly. I was very to discover this, that there's a tactic called apply, right? Which turns, if you have a hypothesis P implies Q, it will turn a goal of Q into a goal of P. And there's a tactic called rewrite, where if you have a hypothesis P if and only if Q, it will turn a goal of P into a goal of Q. And mathematicians at the very beginning just constantly get these two tactics confused because they simply don't think they just know how math works without ever having thought carefully about the details. I found this quite interesting. So I'm talking about beginner mathematicians. It's very interesting to see smart people completely bewildered by very, very simple tactics, because the problem, they see the word apply, and they're like, oh, let's apply this theorem. It's like, it must be the apply tactic because I want to apply something, right? So that's something. And then so that, I'm talking about, learners, and then I mean higher up in the hierarchy. But what do people like me get frustrated with? The answer is that because we can't switch seamlessly between set theory and type theory, right? I mean, you had a question earlier. How do you make a type? I mean, we made an algebra hierarchy in paper format, and there was no fuss about it at all. I mean, it's obviously true that every field is a monoid. I mean, what's the fuss about? So that's something. I mean, we get frustrated about how there are many things which are obvious, which all of a sudden are not obvious. I think that's an easy way of summarizing the situation. So many things are obvious, and yet the system has to be told them anyway.
Anyone else want to address this question?
So maybe that's not a direct answer, because I don't have the experience of being a mathematician and entering to play as a beginner with a proof assistant. But something that can be frustrating when you start using a bit more the tool is the difficulty to search for lemmas and stuff like that. Yet that they should exist somewhere in some libraries, because it's true, it has been formalized, and it's very difficult to search for such a thing. And there are reasons for that, because it's not that easy to make a system of search with dependent types and so on, and conversion and unification and so on. But still, it has to be improved, and I think it's the same situation in Lean and Coq, and even maybe worse in Agda. And it's very hard to find a theorem, even if you're sure that it has been formalized somewhere, but you don't really know the notation, you don't really know the name, and then you're lost.
I mean, one attempt to mitigate. I mean, we made a gigantic monolithic math library with 700,000 lines of code and counting, which is one. So you just import all of it and then search. That is one way that we seem to be trying to get around this issue.
Yeah, but how do you search inside it?
I use the library search tactic, and I have no idea how it works. I know that Scott Morrison wrote it, and it works for me. But
yeah,
maybe
but,
I understood
by the name of the lemma, by the
oh, no, we just
structure involved.
We write the type of the lemma, and then we can search for it in the library. But I'm not really the person to talk to about this. I just know that it works for me in the kind of the domain which I'm where I'm working.
Because if it has been defined by some other group of research, the way they state lemmas can be slightly different, and it will not be found. This is okay when you find lemmas that you have already defined yourself or your collaborators, but if you search in a library that you don't really know and understand, then you need to understand how it has been developed already to be able to search inside it. And it's a bit I mean, that's my experience, but maybe it can be mitigated.
It might just be that somehow we generally mean different things when we're talking about lemmas. Somehow, I think mathematics is just the kind of lemmas that we prove in mathematics might just be different to the kind of lemmas that one does in number theory. Say they might have a different nature to the kind of lemmas which are being proved in the other panelists are proving.
No, but maybe if you try to search for lemmas in the MathComp library in Coq, I think it will be defined in very different ways from what has been done in. So even for finite group theory and stuff like that, it's really a different way of understanding and different conception of this object, and maybe you will be a bit surprised in the way they are even the lemmas that in the way they are stated and so on.
I see. So you're saying that the problem shows up when there are different ways of saying the same thing.
Yeah.
I think somehow we try to avoid we try to make Lean's maths library coherent. We try to write things in simp normal form, basically.
Yeah, but I'm not sure that it can scale to different communities, different libraries, and so the situation in Coq is really the opposite. Is like instead of one monolithic big stuff, we have plenty of small and sometimes big stuff, and that's why it's harder to if you're used to one library, then it's easy it's easier to search in this library. But if you try to search in any libraries that you don't understand or don't even know about, then it becomes difficult.
Yeah, I'm sure it would be. Yeah.
Okay, I think we have time left for at most one question, so let me try this one. What are everyone's top recommendations for improving education and/or outreach to get more people using proof assistants and/or using them more productively?
I take these things into schools. I show kids proofs that 2 add 2 is 4 from Peano's axioms. And when we're way behind Coq when it comes to formalizing geometry, but when we have geometry and when we have Electron, I'm going to be taking this stuff into school and proving basic circle theorems. So I get kids interested from a young age. This has always been my policy.
Seems like it should work well if it works. We'll have bimodal range of possible outcomes. Cool.
So I think we should embrace domain-specific logic, or just like we embrace domain-specific language. Kids want to have a very friendly, very simple, domain-specific language or logic, and the same for the high school kids, or same for the middle school kids. So that's where why my initial opening statement, why a certified ABI is important, because if we have a shareable format that you can map different domain-specific logic into the common ones, then people can develop their own gadgets or tools, libraries in their own logic, as long as they can be compiled to this common format. And then see their work gets used. So it's may not be directly having kids to directly use sophisticated proof assistant, but various of these front end, beta GUI, domain specific logics will offer great platforms for adoption.
Sounds good.
So there's something I can add. So I think there are lots of usability issues in proof assistance, and well, we are kind of just building prototypes, so we have the freedom to change the system dramatically. One thing that we have been trying is to have we have been using cubical type theory, and some of the things that have been preventing people from learning it is kind of complicated cubes that are flying around. One thing that we've been trying is to use OpenGL to visualize the cubes on the screen. And we have been also talking to the people working HCI. There are actually lots of research in HCI trying to figure out what kind of interface can you design. And no, you don't need a neural network behind it. There are lots of already very good rule-based systems that is already providing very good system that could also solve partially of the problem of searching. Part of the issue is like to what degree the system can suggest the lemmas that you want to do. Again, you don't really need a big neural network behind it. Yeah, since you are ending, I just want to add something else. Personally, I'm less interested in computing the Brunelli number too. I think there are many things that we can work on. For example, the usability issues.
Okay, thanks. Nicolas, you want to add anything in here?
No, thanks. I agree with what has been said.
Okay. Well, very good. We've hit the scheduled end of this panel. I'd like to thank all of our panelists and everyone who contributed questions and or just watched our stream here. And in about 2 hours, we'll have a keynote on the OpenAI Codex system. And so we can wrap this up here and use our little applause buttons and thank the speakers thoroughly. Clap, clap, clap.
I would be quite happy to talk to people afterwards. Is that a possibility?
Oh, yes. Yeah, so I would suggest that any of the panelists who are interested can head to the lounge area after this and just sit down at one of the tables there, and people should be able to find you and pick your brain about anything or share wisdom, etc.
Sounds great.
And thank you, Adam.
Okay.
Thank you, Adam.
Everyone. I'm going to close down this session.